as a result of transformation. The most popular transformation can all be considered example if simple power transformation is characterized by the y power lambda. Lambda as a Greek lambda that we would have can take on certain value, and the effect of the power transformation is greater the more lambda differs from unity. So what happens is that when we are talking about the y over lambda, in fact, we're trying to use the y over y power lambda as our transformer. Like, for example, lambda can be 2. In that case, we would say that the result of our transformation is y power 2, right? So here I wrote down y squared here. So we call this one, as I said, power transformations. And all the power transformers, we have like different categories, but we have 2 main categories that we use while we are working with the data analysis in the data analysis section. It's like that we would have the Johnson one or Cox one. They're very similar. The approach is similar. For the Cox one, what happens is that we would say the value of the observation, it's greater than 0. But for the Johnson one, it can be 0, or the equation is different, but it can be 0. Similar, they're similar, but it's different. It can be 0 or negative values as well. So what for the Cox one, we would say that we have a range for lambda, and we will find it by drawing like we would need to find out the optimum value of lambda for that specific experiment that we do. But mainly lambda is very small. It's between -2 and +2. So what if you're working on your research and you think that it's better that if you try to have like power transformer like the Cox method one, consider lambda between -2 and 2, and then it's just that you just put it like you put down lambda equal to -2, you find out the sum of the square, lambda equal to 0.5, -0.5, 1.5, and then 1. Like you can do that like a step by step and find out the related sum of the square. And the one that is going to give you the minimum amount of the sum of the square is the maximum likelihood, right? Method. That one is going to be the optimum lambda that you are going to use for your transformer. But when we are talking about the logarithm of y, 1 over y, square root of y, these are special cases of y power lambda. Basically, we say that if lambda is equal to 0, we would go with the logarithm of y, right? If lambda is equal to -1, it's going to be 1 over y, and if lambda is equal to 1 over 2, like half, 0.5, then it's going to be square root of y. And this is the one that I said that how we calculate the lambda. It's like this one, the example before that we had. But as I said, for our course, the concept behind these transformers are very important, that we would know that what do we, for example, one of the questions that I can give you is that when we are working with the transformers, like Cox, let's say transformer, what are we really changing? Like when we want to start working on that, and then in the option, I would tell you that the structure of the model, the y that we would have, the observation, and we are working with y, right? So we are transforming y here. Here is written, as it's written, you can see. Lambda is like a parameter to be located and estimated. Easy to plot the function of this is the sum of the square of the lambda and z, and locate the value of lambda maximum likelihood value that gives the smallest s, like this s sum of the square. And often there are people that most of the time people plot the natural logarithm of the sum of the square. The trend is going to be the same, and we are looking for the minimum amount of lambda. For example, here the lambda estimate based on this example, like this curve, it's going to be -0.75. What does it mean? It means that my power transformer, it's going to be, I'm going to write down here. When we find out lambda estimate, it's -0.75. In fact, we would say, okay, -0.75. So lambda, my power transformer, or the transformation process that I want to go through that, it's going to be y power minus 0.75 equal to the x beta plus epsilon. In fact, just go back to the board. Okay, good. So when lambda estimate is minus 0.75, in fact, instead of y, we are going to put this term, and the rest is like, it's going to be like before. Like, for example, if we have, let's say in our table, we had like x1, x2, x3, for example, right? And then we had y for the observations that we had. So instead of y that I would have here as my observation, I'm going to write down y minus 0.75. And then I would write down the value, whatever it is. Like, for example, if I had like, this is data observation, right? So, and when you wanna develop our model, if you remember, we said that we are gonna have X matrix, right? And then we would say X prime X power minus 1, all of those methods that we had in chapter 2. And for our X matrix, we had our X matrix, beta matrix, and the Y matrix, right? So if you want to solve this, what are you going to say? You would say our X matrix is equal to the, if you remember the first column, it was 1, right? Because it would represent like, it would be, it will help us to find out beta null. The next one was whatever value that you had for X1. The second one was whatever value that you had for X2, and you would write it down. That was for X matrix. For beta matrix, we would say we would have beta null, beta 1, beta 2, depends on how many that we have. For Y matrix, here, what are we going to write down? Before we had like Y1, Y2, Y3, like the observation, whatever observation that we had. But when we are working with the transformation, what are you going to do is that instead of Y, you would write down Y power minus 0.75. So it's going to be Y1 power minus 0.75. By 2 minus 0.75, by 3 minus 0.75, you see? So it's like that, in fact, by power lambda, whatever it is. And then the rest is exactly the same thing. You will do, you have these are going to give you value, right? Some new value for your observations, then you're going to make your regression model. When you find out your regression model, then you're going to come back here, right? And then you're going to write down our y estimated power minus 0.75 is equal to the x. You find the result of the regression model is going to be the value for these betas, right? So you're going to write down x, like whatever beta null, beta 1, beta 2, the parameter that you find, plus that's the epsilon is like its error. So now let's go back to our note. To find out the value of lambda, what are we going to do is that we would say, okay, so let's find out the sum of a square. And at the end of these lectures, we have the equations that how can we find it. This is sum of the square of the lambda, like the way that we had before, but I'm going to show you the equations. Okay. Here, if the lambda value is 1, then think about it. Lambda value is 1. It's going to be y power 1, right? So there is no transformation. It's like there is no transformation. If lambda is 1 over 2, then a square root, right? If close to 0, then logarithmic 1. If minus 1 over 2, then reciprocal, a square root. Like it's a different one. And we don't need to memorize it like that. We have y power lambda, just put like minus 1 for the instead of lambda, or put like, that's the, it doesn't matter what would you call it as a name of the like transformer. And it's important that we would know that this is the equation that, like this is the transformer equation that we need to use. Usually one has to use reasonable approximations. If the value that gives the minimum of the sum of the square of the lambda z is, let's say, minus 1.2, then lambda can be set equal to minus 1. So we try to round it. Sometimes you may have to do a bit of try and error to the different values of the lambda. to find out the minimum amount of it. Once on the, and this for like for industrial cases when you're working with, it depends on how accurate your model needs to be. If you go with the exactly, like for example, lambda as minus 1.2, the regression model that you're going to have is going to have a higher R square. You're going to get a better regression model comparing to the time that you would round it, for example, to -1. Once lambda is chosen, the response y power lambda can be used for the subsequent analysis instead of z, or if lambda is equal to 0, then logarithms to any base can be used if desired. Such alternative choice do not affect the basis analysis, just the size of the number involved in the calculation. It's like that the amount of the general equation that we get is very similar, right? So eventually, you want to plot the model of the residuals and perform the model diagnostics that we had. If you are uncertain whether or not a transformation may help, then try one to see that if you're going to get a better model or not. And if you do not see a definite improvement in the final ANOVA, like F-test and residuals, you may find that the transformation is not needed. What I would say is like that I would do for my own, like whenever I'm working on the project, is that at least try to consider one transformation. Most of the time transformers they're helping us a lot. Especially if you're working with Python, it's like, it's very easy. You just add like the power transformer, like whatever you have, you just, instead of y, you're going to put that one. You're just going to call it. It's not going to take that much time, but think about it. It's going to give you a lot better regression model at the end. And what you do is that you would have your ANOVA table, and then you would consider the new y as a result of transformation, and you would have ANOVA table for that one. Then you can compare it with the F-test. You will see that if, for example, you will see, you remember the curvature and interaction that we had? Like the interaction and curvature is two things that is going to make our linear regression model to have a curve, right? And so you will see that, for example, if I have my simple linear regression model without the transformation, I would see the interaction is not important. So I'm going to test it to see that, okay, if I have the transformer, like one of the transformer, I'm suspicious about the way the fitted model. I'm going to use one of the transformers based on the distribution of the data points that we have, and then I would see that, oh, it's still the interaction, it's not significant as a result of ANOVA. Then I would say, okay, so I don't need the ANOVA table. It's very simple applying the transformers, especially the power one, the BC one. It's super simple because you just, instead of y, you consider y power something. But the effects of it on your result, it's a lot. So if you do use a transformation, remember to reverse the process when you present the final result. It's like that because you have your y like as a result of the transformer, right? Like y power lambda is equal to that regression. Make sure that when you want to present it, that one is y power something. So whatever you find out, it's a new population. One thing that we have about this transformer is that, and generally for all of them, not just for the Cox one, whenever you are working with you get the normal, you get your data points, and let's say it's going to cost you a lot, but you're going to get your data points, and they are like Gaussian one, but they're a little skewed, for example, to the right. So in that case, transformers is going to help us a lot because it's going to give us the, like, for example, this is good actually. Let me just show it on the structure. It's like this. For example, you get your data points, like observation, and your distribution, let's say it's like this, right? It's a little skewed. So what are you going to do? We are going to use the transformers, like depending on the nature of the experiment that we are working on. And then as a result of the transformers, we're going to have something like a Gaussian one, right? So you can work with these data. The only thing is that you're working with the new y here, right? So here was the y, but here is the y, like y star or y as a result of the transformers, as a result of the transformation that we have. Then you can write down have your regression model out of it, and then you would have like y square is equal to something, or a logarithm of the y is equal to something, or the natural logarithm, or 1 over y is equal to something, right? So that's another application that you can use it. If your research is like you would need to do the data analysis. In most of the research that we have right now, we have the data, at least you have a small section with the data analysis, and I think it's good that we would do our best on it because you're going to get a better result, right? So let's go back to our slides. Remember, statistically speaking, a power law relation like y over pi power lambda is usually triggered by an abnormal plot of residual. And it's like usually most of the time that we would have is we are talking about non-constant variance, the time that the variance, like the residual plot, does like a funnel. Okay, so here, if you are the experimenter, just do not go into the do not go into the lab to start collecting data blindly, and just to see what happens and where you are, and think about your process and what you understand well about it. Like for example, if your process, like if you are working with the blood cells, the number of the blood cells, so you know that you have a Poisson distribution. So definitely you would need to go with the transformer. So before going and collecting your data, it's good that you would know that what's the nature of the experiments that you want to do. What's the, like from literature, you can see the similar trend that you would have. Like for example, if you have the log normal distribution, and they have log normal, variable distribution, all of these ones, if you go at the end of chapter 5 in CSC 220, like in this any second year stats course, we would have a chapter as a continuous distribution, continuous variable distributions, like z value, a standard z that we have, like z table and all of those ones. It comes from the continuous one when you think about the continuous distributions. So, or we call it density functions as well. But in any second year stat course, if you go find the chapter of the continuous distribution, you will see different types of the distributions that we would use in reality. And we would have like for each of them, you can see that you would always log normal. So it's better to go with this transformer. So you know from the beginning, in my opinion, that would help you a lot. Think about what you can measure and what it represents. Think in other words about what data you are planning to collect before you collect them, in fact. It's going to help you a lot, right? So especially when you are working with the design of experiments and you want to have, like, you would know that, like, these are the factors that you have, you can decide which ones to collect. And from a similar experiments, even you can see that which ones are correlated or which ones are aliases together. So you would find the decide which one you want to collect before going to the lab. Based on process understanding, mechanism, first principle, think about your model structure. If you do the above at the design stage, you may cut down the load of your original problem and eliminate many of the related headaches that come after the experiments are conducted by, they would say, 75 to 85%. Of all the bugs that you get after collecting the data. It's like that you are going to collect the data in a more cluster way, in a more organized way, so you know the categories that you are collecting your data in. Use systematic, like, design of experiment methodology that we have. Like, you would have the design of experiments, and then after find out like which ones are aliases and all of them, you would do you will test for the curvature, right? And see that if you have a curvature or not. If you didn't have a curvature, you would go with the steepest ascent or descent. And if you had a curvature, you would go with the response surface methods, like techniques that we had. And then the data analysis and parameter estimations are simplified. You also know what you have done and why, and therefore you can select the next step with more confidence. It's like that you would have a better justification. But this is all about the concept that we have about these on the different transformers and like the transformation. What do we mean by what usually it's like that? It's not, the application of transformation is not just in statistics, right? So it's like with the, we are working for the regression models whenever we are working with the DOE, like the regressions and those ones. So we are going to use this one. But when you think about it, in many math equations, we can use the transformation. It's like the different type of reserves. So here